Hi, my name is Greg. I'm a PhD student here at Oregon State University, and my group studies the optical and electronic properties of organic semiconductors. Now, my research focuses on using fungi-derived pigments for optoelectronics, and it's a collaboration with the Wood Science and Engineering department here at OSU. So why study fungi-derived pigments? Well, first of all, this is a sustainable and naturally sourced material. You can see what the fungus looks like in the wild here. It has this nice blue-green color from the pigment itself. This pigment is called xylendine. And here's another example of that, what a piece of wood in the wild looks like once it's been stained with this pigment created by this fungus. So another thing is that this pigment has shown remarkable environmental stability. Now, if we take a look at this is a piece of woodwork from the 1600s. And you can still see the blue-green coloration in this woodwork. That means that after hundreds of years, this molecule still persists in this woodwork. And lastly, this is totally unexplored as an optoelectronic material. So we want to know, can fungi-derived pigments serve as stable and sustainable optoelectronic materials? So we have several different pigments that we study. Here are the fungi that produce these pigments and the respective pigments. There's this blue-green one called xylendine that I already mentioned. There's also a red pigment and a yellowish-greenish pigment, although most of our work has focused on the blue-green pigment xylendine. So, xylendine's chemical structure has this characteristic backbone, this conjugated core structure, which is key to its optoelectronic properties. Now, this is because when you have a conjugated core like this, the electron wave functions will overlap with each other, and that means electrons can move freely along this backbone. Now, we've also got these OH groups on the side of this molecule that allow for hydrogen bonding, which also affect its optoelectronic properties. And this structure was first determined in 1965, although nothing was really done with it since then. The structure was refined in 2000, and the synthesis was unsuccessful so far, and its optoelectronic properties are largely unknown. So we've taken a look at some of the optical and electronic properties. Here's an optical spectra of xylendine in solution, and we've used this to test the stability of the molecule further. So we took a look at the absorption spectra you see here, compared it with a few other benchmark organic semiconductors, and monitored it after being exposed to light for about 30 weeks. And we see that the absorption spectrum decays just after a few days in certain organic semiconductors. And our stable organic semiconductor, this red one here, it decays after about 5 weeks. However, xylendine lasts about 5 times longer than that. So it's very stable. We've also taken a look at the electrical characteristics by making films on sets of electrodes and measuring the current output with respect to the voltage. So I plotted this here on a log-log plot, and in this region here, we see that it switches to a quadratic behavior. And in this region, we can fit the current characteristics to this equation that you see here. Now this value, mu, is the effective mobility. Now this is a measure of how fast an electron can move in a given electric field. Now this is a key parameter for organic semiconductors. So we want to know what that is. And when we fit this equation to this measurement here, we find mobility values that are in the range of 0.1 to 0.4 centimeters squared per volt second, which is fairly decent for this material. It means it's good enough to be used as an optoelectronic material in devices. Now, we actually believe this to be a lower bound of the mobility, and with better processing, we could actually get a better value of mobility and better performance in devices such as solar cells and transistors. So fungi-derived pigments show promise for stable and sustainable optoelectronics.